Oh, you can tell by this, yeah. Okay. So we're now going to define the value function for the problem 3.7, which is the problem that we started out with in this chapter. But we're going to have a special case, which is objective function replaced by 3.28, which is the correct, which is the discounted form of that objective function. Now, there is one thing here that I have to add one more line to it, which is probably will make the book more understandable. This is not VXT. It is not VPVXT. It is the current value. It is the current value time T dollar VXT. It is not the time $0 VXT. So let's go back. $2.9 on page 33. That's why I wanted you to go there earlier. It is the same place I want you to go. This VXT, it almost looks like we are doing it for 3.7, which is the problem. What is going on is that if you look at page 33, equation 2.9, we define the value function there. That is the present value function. If I were to bring that value function here, I would put VPV on the top of that. But I'm not bringing VPV in this chapter yet. Only HPV and all those are done PV, but I'm not even bringing that. So we didn't define it. But I defined directly the current value. So let's see how we define the current value. We do exactly 2.9. So if we do exactly 2.9, we will define VPV. But in order to define V, I have to do one more thing. I have to multiply everything by e to the rho t. So you see e to the minus rho, and there's a minus t here. So there's a e to the rho t. So on 2.9, if I put f here, f is e to the minus rho s phi of s. Then there is extra term e to the rho t. That is coming because I'm converting VPV of 2.9 to V, which is the time t dollars. Do you understand that, what I'm saying? Anyone?
Yes, it's good.
It's clear. Okay, so that's the ET, and again, there's a e to the rho t here. As you see, minus rho and minus t, there's a multiply by e to the rho t. So I'm going to put a little remark in the book and also in the slide later to say that this is VXT, which is the equal to VPV of XT is given in 2.9. I will write something 1 or 2 lines to make it a little bit clear. Okay. So we now have a time t dollar value function. I may write a time t value function or something I have to do. And then it is almost defined exactly as in chapter 2. Because that's the time we define the value function. We didn't define the value function in chapter 3 because we didn't prove the dynamic programming for chapter 3. But this is coming all the way from 2.9. And this is 2.9 times e to the rho t, and that gives you 3.53. Notice if I don't satisfy these constraints, then the value function is by definition minus infinity. It is because there's no feasible solution. There's no feasible solution, then the maximum value is minus infinity. You cannot do any better than minus infinity. And now I can do the dynamic programming that I did in chapter 2. So what did I do in chapter 2? I took from t to t plus rho delta t. Okay? And then I put e to the minus rho delta t, v of xt plus delta t, t plus delta t. So if you might want to open your book and so you can see this 3.53 is same as 2.9 except there's e to the rho t term. 3.54 is exactly same as similar to 2.12. So we have a 2.12. And we go further. Now, e to the minus rho delta t can be written as 1 minus rho delta t times O delta t. Oh, this should be small O delta t. Why is this? This should be small O delta t. Oh, is that in the book? In the book? See, you always find something here and there when you teach.
Yeah, it is also a temple in the book.
Oh, book doesn't do any. Book, we don't have this. We don't mention this in the book. Oh, yeah, it is. Oh, it's also, no, it should be small O delta t. It's a mistake. Okay, so that's a small O delta t. Sorry, this is also a mistake in the book. So we obtain the current value version as rho v equal to this, equal to that. So you can see that this was 0. If you look at the corresponding equation, 2 point, let's see, what is it? So if you look at 2.15 and 2.19, this side is 0. I get rho v now because of this e to the minus rho delta t. Because when I take it, this will give you rho, the one v will cancel with v, and this will become 0 as delta t goes to 0. So we get one extra term because of the expansion of this guy. And that extra term is very similar to this extra term rho lambda here. So you can see that, so you can actually get meaning of all of these. We define the value function, we got the meaning of that, now we get the meaning of the current value function. And the terminal condition now is psi if this minus infinity otherwise. So I hope this is clear. And if you were to define the derivative of value function with respect to x and call that as a marginal value, then the marginal value will be this lambda that we have. Okay. So now we can write the other conditions in special cases. Free endpoint problem, it is this. Fixed endpoint problem, it is beta to be determined, and so on. And so this is, sorry, this one is what is called one-sided lower bound. If I have a lower bound, xt is bigger than equal to k, this is a constraint of the A type, not B type. And for that constraint, I should have lambda t bigger than that, and there's a complementary slackness condition, and there's a shadow price alpha, which is bigger than equal to 0. And all of this can be derived. And I finally do all of this, and then there's a more general condition, which is this is upper bound. Finally, the general case is y sub t, and this condition was given earlier. And you can derive all the previous conditions using this condition as well. This is important. This is new. Sometimes there's a budget constraint. That means if my state is x and my decision is u and my time is t, then it takes that much amount of money to make that kind of decision. And over time, this could be a discounted value if you want. Over time, the total amount of money that I need to implement that decision is given by this. And suppose I have a budget. and the budget is K, then I cannot spend more money than the budget. So this is a constraint on you, but in a different form than the one that we have had so far. Okay? So it's a constraint. It's not a G-type constraint. It is a different kind of constraint. It's called isoparametric constraint or a budget constraint. Well, it is very easy to deal with. So what I do is I define a new variable, x dot n plus 1. I already have n variables. Now this is the next one, n plus 1. And I define x dot n plus 1 equal to minus L. And I define the initial value, which is the current budget that I have, K. And notice this is the beginning value of the budget, and I'm spending the budget this way. Each time I spend the budget this way, okay? And when I spend the budget, this is decreasing. And I want the final value of this to be bigger than equal to 0, which is same as 3.64. That means I don't want to overspend more than K, which means that the total amount I would spend has to be less than K. So now I have a state, and the constraint is exactly this form. It is a lower bound, and we already have a lower bound constraint given by this form. So I know how to deal with it. Okay? So this is one way of saying that if you have a constraint like this, you can transform the problem and you have a standard problem then. So this is the summary of all the constraints that we have in the terminal value. And we can actually use this table to find the transversality condition of lambda t. Let's continue on. So this is the bequest now. So this person wants to leave a bequest for his children or for charity or whatever at the time t, which is time of retirement or time of death, but is a deterministic problem. If the time of death, this t will be stochastic. But we know how to handle that problem, but not now. Okay, so we have a bequest, and now the problem is I want to solve this problem so the Wt is bigger than equal to 0. I don't specify what it should be. Only specify that it will be bigger than equal to 0. Remember, last problem, it was equal to 0. I cannot have a wealth less than 0 because this is not allowed. That's not feasible. But Wt bigger, well, it is feasible, but it's not allowed. I mean, I'm not allowed. I have no money, so I cannot spend it. I'm not allowing to go bankrupt in this model. Okay, because log CT will kill you if you were bankrupt. So Wt bigger than equal to 0 is the terminal condition. Notice this terminal condition is neither fixed point, not free point. It's halfway between fixed point and a fixed point. So it's somewhat fixed and somewhat not fixed, which means the lambda t should also be somewhat fixed and somewhat not fixed, because you cannot have too much freedom. If you have too much freedom, there are too many solutions, and if you have too little freedom, there's no solution. You have to have exact amount of freedom so that you have only one solution, and that's what we want. Okay, so T denotes individuals dead, BWT is a bequest. Let's go on. So Hamiltonian is given by this. Lambda dot is given by this as before, but now I have a discount rate, and I also have R, so I have both of those things here. And here's the terminal condition. You can see table 3.1, row 3, lambda t is bigger than or equal to b, lambda t minus b equal to 0. How to solve this problem? Well, here's an idea. I solved the problem when Wt was required to be 0. When that was required to be 0, lambda t, I had a value of lambda t which was beta. That beta was this value. That was our previous solution. clearly, if that beta is bigger than b, because this is now b times wt, it is not the function is defined to be linear. Okay, if that wt was exactly, if that beta was bigger than b, then this condition is satisfied, right? This condition is satisfied, and when this condition is satisfied, um, the same solution is good. That means that the previous solution is still optimal. That means that I will leave zero wealth. It means that my B is not so big. Because my B is not so big, I don't put too much value on my children or charity. And so I will spend all my wealth and leave nothing. So the previous solution is still good. But suppose this beta is not bigger than B, which means B is bigger than beta, which means that I put a lot of value on charity. If I put a lot of value on charity, then the previous solution cannot be good, because if I put a lot of value on charity, then I should leave some charity. Then our previous solution also allows us to solve problem this. Then what I do is, instead of, because beta is less than B, now I'm in case 2. Well, in case 2, I just set lambda t equal to B. Initially, it was beta, which is beta, which is bigger than B. Now I will change lambda t to exactly beta. No, exactly B. I'm sorry. If I put exactly B, then I will find out what the WT would be. Right? So what I do is I put exactly B. Then lambda t is given exactly this way. We already know that lambda t is given in terms of beta. So I put beta equal to B, I get this. Then instead of beta, I have a B. So my C star is T is going to be equal to this. Remember, this beta, when the beta was too small, when beta was small, I consumed a lot and I left nothing at capital T. But now I put B, and B is large. Remember, now B is larger than beta. So I'm consuming little less than what I was consuming in the previous example. And the reason I'm consuming a little less is because I want to leave some wealth. So then, given that C star, I can solve for W star T. And when I solve for W star T, if I put small t equal to capital T, I get this one. This is bigger than 0. So since this is bigger than 0, this satisfied lambda t equal to B. And this becomes 0, and this can be bigger than 0, but this is equal to 0. It's still equal to 0 because the product, even though this is positive and this is 0, the product is 0. So everything holds. Okay. So, and this is just a remark that you can do it alternate way, but it's the same thing. So what I did was I solved the previous example. I built my solution on the previous example and the previous solution. If I did not have the previous solution, I can go like this. I can start directly and then go through, and I'll get the same equation eventually, but I get the solution. So we're done with this. Now I have another example. Now I have the old example, but I have now x2 bigger than or equal to 0, and I have a control between -1 and +1. Sorry. Hamiltonian is minus x plus lambda u star is bang bang, lambda dot equal to 1, so I can solve lambda dot directly. And the condition on lambda is this. So I don't have the exact condition on lambda 2. I have some condition which depends on x. So I can solve in some way, but I cannot really get everything unless I know what x2 would be. So let's see how we do that. Here's how we go about this. Nowadays, lambda t is increasing. If it is increasing, then the control can only change from -1 to +1. It can never go from 1 to -1. And notice this is monotonically increasing. So the control can change only once, at most once. So either it could be -1 and then change to 1, or it could be -1 all the way, or it could be +1 all the way. Those are only three possibilities. Okay, and going from -1 to +1 with a change time, where switching time will allow the other two also, because the switching time can be 0 and switching time can be 2. And with those switching times, the other solutions are also allowed. So I'm going to then say, let the switching time be T star. That means my control is -1 up to T star and a +1 after T star. Notice if T star is 0, then control is +1 all the time. If T star is 2, the control is -1 all the time. So all the controls are allowed. That means 3.75 allows all the control that would satisfy 3.72. Okay. And I assume T star to be less than equal to 2, certainly bigger than equal to 0. So far so good. Notice T star is a switching point. So lambda T star has to be 0. Because exactly at lambda equal to 0, this control will switch. So lambda T star has to be 0. If lambda T star is 0, then the solution of this is exactly given by this. See, lambda dot T is exactly 1, and lambda T star is exactly 0. So this is the solution of this differential equation. Given that we switch at T star. We don't know if it's optimal. But given that T star is where we switch, this is lambda T. So now we have to find out, there's only one thing left now. The only optimal thing to decide is what is the value of T star. So this is the next two cases. Either T star is less than 2 or T star is equal to 2. Case 1, lambda 2 will be 2 minus T star because T star is less than 2, and lambda 2 will be then 2 minus T star. Because lambda T is T minus T star, lambda 2 is 2 minus T star. 2 minus T star is bigger than 0. And then the complementary slackness condition said that if this is bigger than 0, then x2 has to be equal to 0. So with that, we solve for xt. How do we solve for xt? Well, we solve for xt by setting u star -1 up to T star and +1 after that, and making sure that x2 equal to 0. So I solve x for x2 equal to 0. I get xt equal to 1 minus t for this. And then starting from T star, I resolve this equation again, and I get this. So I have a whole solution for x2. Then I made x2 equal to 0. I put that condition, and I get this. This says T star is 3 divided by 2. And since this satisfies that condition, I'm done. In an exercise, you're asked to assume this and show that this does not give you the solution. Okay, so you might take this case first, then there's no solution, then you have to come back to this one. In the book, I always take the one that works, so I don't have to spend another page. Once you have that, x star t is given, and I can write this as the solution. So x star goes from 1 to that. At 3 divided by 2, it switches and goes all the way to 0. Lambda starts from here and goes all the way at the slope of 1, and then at 3 by 2, at 1.5, it becomes 0, and continues on, and the lambda 2 becomes half. X star t like this. Now, in this book, in this edition, which are certain things which are new, they were not there in the previous one, is I've done a lot more work in this book to put marginal values and give some idea, because those are important. If you write a research paper these days in any of our journals, they don't want so much math anymore. They want math to go in appendix, but they want you to give you intuition. What is the meaning of everything? And this is where all these marginal values and all these things come in. So we are now going to do some longhand exercise of telling you what is the marginal value and how the marginal value. So what we want to do now is the following. We want to show that the lambda, in fact, is v sub x. That means there's a value function, v sub x, v of x, and then if I take the derivative of that value function with respect to x, I get lambda, provided the v of x is differentiable. Okay, so this is what I want to do. So let's try to, this is not so, it requires some work, so let's just do that. So what I want to show is take any point x and any point t and try to find out v of xt. How do we do that? That means we start with a t with initial condition x and we resolve the problem. When we resolve the problem, we get the value function at that time t. Okay? But it turns out that we cannot take any x and any t. And this is where I'm going to switch to whiteboard. Min, where's the whiteboard? Oh, there we go. Notice that I have to have x2 equal to 0. And for x2 equal to 0, I have to start, I cannot start here. Because if I start here, even if I use the control 1, I can only go here. I cannot go here at time 2. So in order to get time 2, my x has to be above this line. Okay? So let's take an x here, which is this x, and a t here, which is this t. If I take this x and this t, remember the solution. Remember the solution was going from 1 all the way to there and then go there. That was the solution. So the solution will be similar. You go from x with a -1 all the way up to here, and then with a +1 go all the way up to here. And so your optimal control will be -1 up to here and +1 up to here. So given x and t, I have to find out this point. I have to find this time t at which that happens, and I have to then go all the way up to here. Then I have to integrate all of these to find the vxt. Okay, so this is kind of the idea. So let me also mention to you that I only took some x and t. There may be some other places you take x and t, which may give you a different solution and may give you a different kind of valuation. So I give you just one example, and we will go back to the slide. So given that xt, my control at any point s, and this xt is the initial condition at time t. So I'm going to write that control given that initial condition, and this is the current time s. Okay, so -1 when s is in this interval, and +1 when s in that interval. That means given that it's easy to compute this and easy to compute. So I can compute that, and that was given by the formula there. And then I can basically go, you have to do that at home if you want to. So this is that point, and from that point on, it is 1. Okay, so this is fairly easy. So I have a control -1 +1. Once I have a control, I can find out the x star given this initial condition xt at any time s bigger than t. So s is bigger than t. It goes from t to 2. So this goes from s goes from t to 2, but in 2 parts. So I solve for x star in this part, then x star in this part. So far, so good. When I do that, I can now, for x bigger than t minus 2, find vxt. But what is Vxt? Well, it's the integral from t to t of x star. So let's go back to the problem. The problem says minus x dt. That's what I have to do, right? And I have to now go from t because my problem begins at t. So I go from t and I integrate minus x dt, the trajectory. So this is minus x star of xt. Xt is our beginning initial condition. STS, this is my integral. This integral can be, because I know x star t, these are very easy to integrate. So I integrate these guys, I get this and this, and I finally get this. So this is in fact the closed form solution of Vxt for any xt for any x given bigger than t minus 2. Remember, I needed x bigger than t minus 2. So there is for x bigger than t minus 2. Oh, sorry. Yeah. So I get this. For x less than t minus 2, there is no feasible solution. So Vxt is minus infinity. Now notice, we can only verify this solution for 0t less than 3/2. Why? Because if I go beyond 3/2, I may not have this part. I may not have a switch point. I may just go like this. It's a possibility. So I did not do all of that. And that means there are still parts of, remember, dynamic programming says I need to find Vxt for every x and every t. But you can do that. I'm only doing for one x and one xt. And there are some other places you can do afterwards. So only from 0 to t less than 3/2, I can do that. Okay. The value function Vxt is continuously differentiable, and x star t is 1 minus t. This is our solution of the problem. And I'm going to now take the derivative of v sub x at x star tt. So this was my optimal solution of the original problem, starting from 0, times 0, and starting at value 1. And I'm now, so what I'm trying to do, so this is interesting. I need to find the v sub x, value function x, along any x on this point, and then any x on this point, and x here. So the value function is defined, and the lambda is defined only along the trajectory. So in order to define the lambda along this trajectory, I have to compute the Vxt everywhere, and then substitute this value in for x. That's what I have to do. Okay. I cannot compute Vxt for this value of x because I need to find the solution for each x in order to do that. Okay. So I have a v sub x from here, and I substitute x star t from there. That's what I'm doing here. So v sub x, from this one I get minus half of x. You see it's getting minus half of x. And from here I get half t. Okay? And from here I get minus 1. So this is minus 1. From this one I get half t. This one I get half x. But I put, instead of, for half x, for x I put x star t. X star t is 1 minus t right here. So I put 1 minus t here. So I get all of that. I put that because t minus 3/2. And you see lambda t is 3 minus 2. 3 minus lambda 3 is t minus 3/2. Let's go back. Why did I get lambda here? T minus 3/2. That's the lambda we got. So now, doing all of this, now we have actually do the dynamic programming on this one, full dynamic programming on this one. I took the derivative of this and find the solution t minus 3/2. Okay. You can also try to find a solution at this point to see what happens. Turns out at this point, the value function is not differentiable. So I cannot give you the marginal value at this point. You see Vxt will now be differentiable at this point. Okay. There will be a case there later. We're not going to finish today, but let's see. Let me go fast on this one. This is the condition on T if I need to optimize over T as well. And this is the condition 3.15 when there are no other constraints on xt. Okay, it's a simpler case. So I want a special case where there are no other problems and no other confusion, just a simple case. This simple case, the transversality condition on T is given by h plus this. Notice I told you one way to derive this is to solve for any T and then take the derivative of J with respect to T and put that derivative equal to 0, you get this. And that one is done in a general setting, and it's not so easy. It's done by this paper by me and my postdoc Hartle, former postdoc who was in Vienna. And we wrote a paper in 1983 to derive this condition that I just give you by a formula, by solving for T and then taking the derivative and getting this. There's also another way, and the other way is like this. Let's take a time between T star minus delta and a T star plus delta. Remember, I want to find the optimal T star. To optimal T star, I have to show you by kind of something called first order condition that if I go this way, I decrease the value. If I go this, I decrease the value, right? So both sides, the value will decrease. And so this will be optimal T star. So what if I stop the problem here? So what I'm trying to say is my problem is T. I found the optimal to be T star using this condition. Now I'm saying, what if I stop the problem at T star minus delta? What do I lose? What if I solve the problem all the way to T star plus delta? That means go a little bit further. And then what do I get? And I show that both way I lose. This is what I'm trying to show here. So when I solve the problem up to T star, I have a control U star T. What I'm going to do is from T star to T star plus delta, I have I have a control all the way up to T star. But I have no control from T star to T star plus delta because I didn't solve that problem. So what I'm going to do is I'm going to substitute U star T, constant U star T star in this interval. That means I use the same control up to T star. Then from T star to T star plus delta, I use exactly this control. Okay. So clearly U star is continuous at T star. And X star T is going to be differentiable. So I solve X star T from 0 to T star plus delta using that control. And then I can find J of T from 0 to T for any T in this, because I have now control I have a control up to here. So I can use that old control and integrate only up to T star minus delta. Or I can use all the way to this by using this control in that interval, and I can also use the integral. So I can now define J of T in any of these time, okay, given that control. Because U star T is continuous, X star T is continuously differentiable, and so is JT, so I'll now take this derivative. And I want this to be 0. So if it is not 0, then it will be this or this. Now see what happens. So since T star is optimal, satisfy this. Otherwise, we would have this or this. The former situation, which is this one, would allow us to find a control on this interval. This means that I can increase the objective function value from what I obtained when I did the T star. Because it's not optimal if it's this, then I can increase. Well, then I can find an optimal solution which would give me the value on this, and that whatever that value, this will give me JT bigger than JT star. That means T of any T beyond T star, I will have a bigger value. And so T star could not be optimal. Since the choice of an optimal control for 2.4 defined on interval 0 to t would only improve the value of the objective function. Likewise, the later situation, which is this one, would allow us to find a t for which this is bigger than jt star by taking the derivative of 3.78. Now I take the derivative of 3.78. We can write 3.79. We can write this condition by taking the derivative as this. So first derivative comes from here because I derivative inside the integral, I get f. Then I take the derivative of this. So I get sx x star dot t. It's a full derivative. So I take the derivative to x, then x with t, then st. So I get that equal to 0. And that let's see what happens now. Yeah, and that is, and I put this in lambda. Once I put this lambda, this is Hamiltonian. And this Hamiltonian st, I get 3.77. 3.77 is h plus st. Okay. So this is the argument to get there. Yeah. What this statement here is a little bit subtle because what I'm doing is saying that even with this control that I arbitrarily did in the small interval delta, I can still get this. But if I were to optimize this also, I can only do better. So certainly this will continue to hold. And that means that given this, I can find another t. And so this t star could now be optimal. So what we're saying is for optimal t star, this should be satisfied. And if this should be satisfied, then this should be satisfied. If this should be satisfied, then this should be satisfied. So we're done with that. If we have T star bounded between T1, T2, and some of the exercises in this chapter have this thing, then that condition is like this. Interior solution, it is 0. If it is not interior, then obviously it will be this way or this way. And you can actually figure this way and this way by drawing a picture. I will do that later. If how this goes is simple because if it's less than 0, then basically what it means is that well, there's another way to look at it. Another way to look at it is, let me see where we have to cover. Is that clear to you? Or do I have to say something? Because interior solution, if the boundary solution, if it was less than 0, then I said at T1. If I bigger than 0, I said the upper value. The way you do it is, well, let's do that. Whiteboard. There's a whiteboard. Yeah. Let's erase this. Okay. Okay. So if I want to maximize the function, this is the maximum. And there's a tangent. Excuse me. So I'm saying that if it's the interior solution, that is 0. The derivative has to be 0, so the derivative is tangent. Now suppose I want to maximize in a boundary. So suppose my boundary is this. So my solution has to lie between these two. The optimal solution is here, but now I'm in a boundary. So you can see that because this boundary, the slope here is going this way, less than equal to 0. And then I will set, because this is on this side, this is my solution. And that solution said the slope is this way. Because I don't want to go there because it's decreasing all the way, so my solution will be even less. So that says that if I'm on this side, I take this boundary as a solution. Suppose my solution is this. Then clearly this is not good. If this is the optimal solution, which is unconstrained, so my solution will be this boundary. And this boundary, as you can see, the slope is going up. And that's what the Lagrange multiplier does. So if you take the Lagrange multiplier, without the Lagrange multiplier, without the constraint, this is the first order condition. With the Lagrange multiplier, the solution is here. So the Lagrangian, what the Lagrangian does is it makes it 0. The derivative of the Lagrangian makes it 0 because the slope of this is positive. But then there's a Lagrange multiplier that compensates. It's called compensator, and so it compensates exactly so that the Lagrangian multiplier Lagrangian tangent with the multiplier is still 0. So that's basically what happens. So you can always check these ones by this kind of argument. So now we have solved the problem. This goes fast, and then the next one will be a little bit. Yeah, we'll try to see. So let's go fast on this one because it's not that difficult to solve. So I have an xt here. I have a t bigger than 0, so I want to find control u and also maximize over t. So Hamiltonian, lambda t equal to 1, optimal control, and so u start equal to 1 up to t minus 1 and 0 between t minus 1 and t. But we don't have a t yet. It's for any t, any given t. So now we have to find out what is the optimal t. Well, the optimal t, I have a 3.77, we derived. And we have a u star t star equal to 0 because I need u star t star in the solution. If you look at 3.77, you will see that it has a u star t star term in there because the Hamiltonian is there at t star. So when you substitute that in the 3.77, you get this. And when you get this, you will see that uh, 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 this is exactly x star t star minus 2 equal to 0. When you substitute everything, you get this. Okay, you can do that. Book doesn't give you this, but book simplifies all of that. It just uses 3.77, simplifies all the way to here. And then you substitute u star t in 3.83, which is right there. And then you integrate x, you get x star t. And then when you have x star t, you apply this condition because this is a condition for t star to be optimal. So you put x star t star together with this, you get t star. So t star is now 10. So here's a problem in which I have optimized over u and I optimize over t. And you can see that optimal control now will be 1 up to 9 and 0 from 9 to 10. This is a classical problem. And in this problem, we are minimizing time to go from somewhere to somewhere. Okay. And this is a celebrated problem in the literature, and I think that most of the control theory courses cannot be completed without knowing this problem in some way. And so we're going to look at this problem. The way you look at this problem is the following. The problem is given by x0 and the velocity. So I have an initial position and initial velocity. The position is given by x0, velocity is given by y0. And acceleration by which I increase or decrease the velocity is acceleration is given by u, and u is my control variable. Okay, so usually our standard optimal control problem do not have this kind of differential equation, but we can always change this kind of differential equation into two first order equations. It says x dot equal to y, x0 equal to x0, and then y dot, which then becomes x double dot, is u, and y0 equal to y0. So this is the position, this is the velocity, and u is between -1 and +1. So I can have a deceleration of -1 up to, and I can have an acceleration up to +1. So you can define the optimal control problem is minimum time to go. So what we're trying to do is going this way. We're going from x0 to origin. So I am somewhere, and I go to the origin, to the point 0. And when I go to 0, my velocity has to be 0. I mean, I have to come to a stop. Okay? And so go from x0 to 0 with a stop at 0 with the initial velocity y0. Find the minimum time to achieve this. This is minimum time. See, if you take integral, that is max of minus t, and max of minus t is minimum of capital T. And t is now variable. So I have to define t and a u. I have to find t star and a u star. Let's look at it this way. Before I go, because it'll be more important for you to look at this, and then, so whiteboard again. Oh, how do I get the whiteboard? Yeah. So here's what we are doing. It's a straight line. Okay, I don't know how to do a straight line. And this is the origin. This is a train station. Okay, the train can be here, which is x0, or the train can be here, which is x0. Its velocity, if you're going this way, could be here. So this is the velocity. So this is the x space. This is the velocity space. So the velocity could be here, could be here, could be here. But the velocity here means it is going in this direction. That's what it means, because the train is now traveling in this direction. Traveling in this direction, I want it to come to here and stop. It's a station, so it has to stop, but otherwise passenger cannot get off. So it has to come to a 0 velocity. So I have to change the position and decrease the velocity, decrease or increase or whatever I want to do, eventually get to 0 here. Okay, so that velocity could be here, could also be here. Maybe train might be going this way in the beginning, and then I have to still to bring it here. So the train, if it goes this way, then I have to go like, maybe go like this and go back to here. If the train could be here, can go like this and then come here, and the velocity could be here or could be there. Okay, here means it's going this way, here means going that way. Okay, so that's the situation. So I can, my position could be here, 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 here. That means I can have a different initial condition and different initial velocity, and I want to come to here where this this axis has to be 0, and that velocity goes to 0. So that's my program. So the Hamiltonian. So let's first quickly do the Hamiltonian, and then I will do a picture. -1 lambda 1 y lambda 2 u. That's lambda 1 dot 0 because final position is fixed, so lambda 1 is beta 1 to be determined. Lambda 2 dot is minus lambda 1 dot because it's derivative with respect to y. And final position is finite velocity is fixed, so this is another constant to be determined. And so we can integrate these equations to get lambda 1 and lambda 2 in terms of these constants. And in terms of this constant, bang-bang control is given by that. So far, we know the form of the bang-bang control, but we don't know beta 1 and beta 2. Oh, sorry. We don't know beta 1, beta 2. But we have one more condition. This is the condition of 3.15, which is the transversality condition for T to be optimal. That condition says H plus ST equal to this equal to this equal to 0. And which together with bang-bang control says either this and that or this and that. Two cases here. And at this point, it is better to go to a picture. See, these are various cases and how you get to solve them. But before you solve them, let me show you what we are looking at. If you look at this, these equations, they give you this kind of a manifold, which is kind of this equation, which is like a parabola, okay? So if you go to the next slide, you will see some kind of this parabolas. Okay, and you can see these kind of parabolas. So here's what's happening. Suppose I am here. That means I'm literally at this point, and my velocity is this high. And I want to stop here. So what happens is the velocity is very high. There is no way I can bring the train to stop here. See, I'm here now, but the velocity is still very high. So the train goes past the station. It overshoots all the way up to here. At this point, the velocity is 0, but it's moving in this direction now. Okay, so it goes like this and then reverses. Okay, and it reverses up to here. So this is still the deceleration. I keep decelerating, I keep decreasing the velocity and keep decreasing the velocity. Even at 0, I keep decreasing the velocity, so going backward in this direction because I'm decreasing the velocity. Decreasing, I'm decelerating. So the deceleration is, acceleration is -1, so there is a deceleration, okay? So I come to here, this is another parabola. And at this point, I switch it to +1. That means now my velocity is going in this direction, and I want to now accelerate. Okay, I want to accelerate and come here. No, I want to no. I'm sorry. This is u star +1. So +1 means I'm gonna go in the okay. The acceleration is +1, but is that in this direction? So I'm going to slow down. That means I'm going to slow down means I have to put acceleration that is on kind of this side. So I'm going to slow down and come here. And I'm going to stop at 0. So this is the control from here. It goes here, go here, go there. If I was here, it will go here, then go there. So that's another control. But on the parabola, I don't need to, if I'm on this function and on this function, I don't need to switch. So if I'm here, for example, I simply go like this. So first, the solution tries to find out these two curves. These are the curves that are so nicely situated that if the train is on those points with that position and that velocity, or that position and that velocity, you can just use +1 and go here. If the train is here, it is going too fast, So you decelerate and slow down, slow down, slow down, slow down, and go here. Here is going in that direction. So you slow down, slow down, slow down, slow down. No, I'm sorry. Here is plus, so it's going in that direction. You slow down, slow down. Here it is going in that direction, but it's going very fast because this is the negative velocity is in negative, so it's going in that direction. So you slow down, slow down, slow down, slow down, come here. Once you get these two, you get these parabolas. From each position, you get a parabola and an intersection point. From each position, you get parabola and intersection point. Here's the equation of this parabola. And from that position, you will go -1 up to here, then +1 up to here. So the idea is to determine these parabolas. And for that, I need to determine beta 1 and beta 2. So I think we can finish this problem, but we will not be able to do some more things that are not many left, but we will see. So once you have that, it goes fast. So we have these two guys. So once we have these guys, this is called the switching function. This is those two functions where we switch. So that switching function is a linear function of remaining time. It can sign at most once. And so you have two cases, either -1 or +1. -1 from tau from t to t star will give you, once you put u star -1, I can solve for yt and xt. And I solve for yt and xt, I can substitute for t star from 1 to here. I get an equation like this. So that is gamma minus. And if I on this side +1, that is gamma plus. So that's gamma minus, and that's gamma plus. So far I got that. Okay. Now notice this problem is not so simple to solve. And I'm using maximum principle through and through. And I'm going to give you an optimal solution. So you can sort of see the value of the theory here. It is not so easy for me to simply guess this solution right away. I'm guessing these through the help of this. I get a parabola like this, so I can draw that picture. Okay. Once I have this, I can sort of see what is going on here. So that's the velocity. The velocity when x is bigger than 0, velocity when x is less than 0. And so if the initial state doesn't lie, initial state is not 0 and lies on a switching curve, then we use this on plus gamma plus, we use this -1 on gamma 1, and we are done. So this is the easy part. If I'm not on that, then I am on one of these points. And so while I have a solution, I have to still compute this. I have to compute this point. I have to compute this point and all of that. So that's what I'm going to do. So for this example, this is -1, 1. This is 3, 2, 0. This is, so all of these have been computed. For this example, you can compute this you can compute this. And so you can compute this. All of these can be computed. Okay. So let's just do that. So if x0, y0 lies above the switching curve. So I'm now taking a point like this. It's above the switching curve. These are below the switching curve. This is the switching curve. Above, below. So I'm taking above. Below is the very similar. So I'm going to take above. I have x0 and a y0. I integrate these two equations because remember above this curve, my control is -1. So I can integrate. When I integrate this -1, I integrate. I get this. And if I eliminate t, I get that curve. So if I eliminate t, I get this parabola. So now I have this parabola and this parabola. So I can easily find this because it's the intersection of those two parabolas, right? So I can find this point. That's what's going on here. So I have this parabola, and I can solve with that gamma plus. That's another parabola, and I find x star and y star. So you can see in the picture, when I solve this parabola and this parabola, intersection is given by this point. This is the point at which I will switch the acceleration from -1 to +1. So this is done, and I can find t star because I already substitute this t. So when I substitute here, I got this. Now I got x star and y star. I can put x star, y star back, and I can find the t. Okay, or I can just put y star here, and I can find t. So t star is just y0 minus y star. This small y, the y lower star, and I get t star. So this is the time at which I get to switching point. Total time. The total time is the time that goes from here to here, and then time from here to here. So it's the sum of these two times. I already know how much time is this. I already got that. T small star, T lower star. I have to find this time. So this gives me a capital T star. So the capital T star is that T star, and then minus y star, which we already find out earlier in the table. In the table, I found this time, and then I can add those two, and I get this time. And if I x0 is y0 equal to 1, 1, I can put all those values in the formula that I just did. So I can find all of this. So what I'm trying to now do is, starting with this, I found this, I found this, I found the time to get there. And then I apply all these formulas, starting with 1, 1. That's my, this x0, y0, this is 1, 1. So I start with 1, 1. The parabola is given by this 2x equal to 3 minus y squared. And this point is given by 3 by 2, 0. This point is given by this. So I can find all those points. And then you can complete the solution by finding lambdas, because all the equations are there. And once you find these lambdas in one, you know that given all the u star, you can find betas, and you're done. So this is kind of, once you have the idea of the parabolas, it becomes a simple problem. I'm not going to finish this, so I'm going to spend 1 minute to tell you what is going on. You're going to read chapter 3, chapter 4, and we will start with this, and then we will go to chapter 4. But this is when you have infinite horizon. In infinite horizon, we are looking for, this is, I think Kai or somebody asked that question. So I have infinity here, I have a discount rate, I have an equation, I have a constraint. How do I solve this problem? Okay, so we need to go to what is called as stationary solutions. So we go to get some stationarity, the transversality condition, and then we'll have to solve a problem which goes from 0 to infinity instead of 0 to capital T. And now, of course, there is no terminal value, but we need to constrain. We cannot ask this guy to just keep consuming and let the whole society go down with him, because then he will keep borrowing all the way to infinity, and then he dies, and society cannot recover anything. So we need to put a condition that he has to remain solvent all the way to infinity. So that one, then we got to an idea of a turnpike or a long-range stationary equilibrium. So that is another thing that we will be using. And then we will, again, solve the problem for infinite horizon, give some definition of what's called golden path. That one is not necessary to cover, because it basically tells you that if the problems are this form, then current value equation this form, and the form of the optimum analysis is bang, 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 and singular. So it's just giving some special cases. I don't always go back to it when I have a problem to say, okay, go to table 3.3 and use this, because we can use this Hamiltonian and they come anyway this way. So we don't have to always go back to the table, but this table does this and give you some summary of different kind of problem that arise. And that's sort of what the chapter is. So there is not much left to be done, but we will start next lecture from Infinite Horizon, from this slide, whatever, 68. Any question before we leave? No question? Okay, then thank you, and we will see you